Anyway, welcome to our tutorial on using the Waller Watson Libraries for Analysis, Program Analysis Framework. I'm Julian Dolby. I'm one of the creators of Waller, and there's Joanna, who is a professor at Notre Dame, and who has actually used, unlike me, has actually used Waller for teaching. So in that sense, she is well qualified to give a tutorial on how to use Waller, since she does this with her students. So there we go. I'm going to start with a brief outline of the tutorial. That's roughly classified into a couple of sections. There's the basics, there's how to set up Waller, how to use it, basically doing basic program analysis concept, building a call graph, pointer analysis, building a system dependence graph, things like that. And then the next section is, well, for lack of a better term, we call it advanced topics, but really it's more examples of using Waller, ways of taint analysis. Some of them will show you a couple of ways of doing taint analysis that actually illustrate some of the analysis infrastructure that Waller provides, including Graph Reachability and IFDS, things like that. And then we will talk a bit also, that's the data flow analysis, and we'll also talk a bit about how Waller is increasingly used in the context of AI for code, where the idea is that you take the different sorts of graphs that we can build from traditional program analysis and use those to drive machine learning, often with graph neural networks, sometimes with transform points. So we're going to, that's roughly how it's split. And the first part is going to be in the first session before the break, and then the second part mostly will be in the session after the break, although it will be dynamic. To some extent, it will be a dynamic based on whether we have questions and how it goes. And especially given such a small number of people, it makes total sense for things to be as interactive as possible. And it's really much better if we start saying something and it doesn't make sense. It's much better for us to be told that and allow us to try and make it make sense, rather than try and get moving on having confused people about something basic. The materials are built over time. So please feel free that if we are talking and we are obsessed with our slides and not paying attention, you raise your hand, shout, throw something. I don't know if anybody goes any fruit, but whatever, you can get our attention. So with that said, let's start with an overview. And this is basically about what is Waller in total, how does it fit into a broader ecosystem. And so basically, this example figure shows you roughly what Waller is, and it's roughly split into horizontal and vertical. So horizontal is the languages. We have Java, we have Python, we have HTML, which you think that's not a programming language, but it kind of is, because you take the HTML and the JavaScript together, you get the semantics of your web page. And that's what we mean by when we say HTML. And then there's also plain JavaScript, which also, so Waller does those 4 languages, although those are the ones that are exposed to the world right now. And the way it works is we didn't actually write parsers and type checks and whatever else for all 4 languages. We actually use existing infrastructure. So for example, for Java, we use a bunch of support from Eclipse JDT for things like parsing, type checking, things like that. And after only that, we use the results of JDT. But for Python, we use the Jython tool system. For HTML, we use Jericho, and then for JavaScript, we use Rhino. Each of these has the ability to produce something AST-like, which is what we do. Once we have those, but those are very language-specific ASTs. Once we have those, the next step is to build our common abstract syntax tree, which is essentially distills the AST down to a common notions, ifs and whiles, go-tos, and that sort of field reads, and local reads and writes, and that sort of thing, scoping, that sort of stuff. And each of the language-specific ASTs is converted into that with just a little bit of language-specific glue left for things like, if you think about the common abstract syntax tree for a function call, well, these function calls are very different in these different languages. So there's a little bit of language-specific glue for each language, but the overall AST is very much the same. From that common AST, we then build our own internal form. We'll see illustrations of that a bit later, but it's basically a control flow graph in static single assignment form. And on top of that, you can build things like just get use or whatever else you want, structures like that. So that's core of the IR, which is used for building things like call graphs. And then also from the IR, we build things like program dependence graph from the IR, and then the system dependence graph, program dependence graphs. We also use the we also have IF support for IFDS. We'll come back to that a little later in the tutorial. And all of that is built on top of some more basic libraries that are useful in program analysis and other things. For example, graphs, the bit vectors as well. Things that are just designed, it's their foundation in a way. Everything else is built on top of those, and those can also be used if you are, for example, if you're building some other data structure of your own, which looks like a graph. Well, it has a bunch of support for graph libraries, graph algorithms, which can be applied as well. So to look at that in a slightly different way, the system is very much built on reusing as much of what's out there as possible. So on the left here, we have tools like Eclipse and Rhino. Those generate ASTs. We also, in Voila, we also support bytecode library. We also read bytecodes. Voila originally started reading JVML, the Java bytecode language. We also have support for reading CLI, which is the advanced bytecode library for Microsoft.NET. And we also have support for reading the bytecode of Android, Dalvik, which we read that as well. Because by the time you get an Android APK, the bytecode format of that, it does not use the Java bytecode format. They have their own Dalvik, which we can also read, and then we read ASTs from Rhino and Eclipse. And the first piece that's really us is the front end. That's job is to take the language specific AST from somewhere like something like your language specific things from here, these language specific ASTs, and convert them into the common abstract syntax units. And basically what that does is it's really still in an AST format. It's got the tree structured thing with loops, and it's very syntactic. But it cleans up a bunch of things, so break and continue get turned into go-tos, and just does this because every language has slightly different ones, and it's all standardized to something that's a lot easier to convert to a control flow graph. And so that, which is what cast is. And from there, we translate that into the AI. And it has support for translating fairly complex ASTs. We have has support for unwinding, replicating finally blocks, handling go-tos in and out of finally blocks, that sort of thing. Basically, this is what different languages ultimately end up requiring. Now, for JVML and the Microsoft language, we have a tool called Shrike, whose purpose is to take the bytecode language and generate the same IR. And the biggest piece that it does there, for example, for Java, the biggest thing it's doing there is it's unwinding the stack and going back to a register transfer kind of thing. And as it does that, it does SSA conversion as well. So this translation is doing SSA conversion. This one is doing SSA conversion. Now, it's a different translation from Dalvik, and the reason is that isn't a stack language to begin with. So the translation, the way of building in the SSA and port-based IR is different. And once we have the IR, that's what all the analysis is, the control flow graphs, pointer analysis, that sort of thing. So that's sort of the structure of Voila. And one thing that the reason it ended up like this is over time, we started with JVML. And then we wanted to support similar kind of analysis for JavaScript, got the source from it. And then after JavaScript, other languages become, I think Python could be added here now. And we've been gradually building this infrastructure over time. And with that being said, I think Joanna is going to tell us about some of the basics of building stuff.
All right, so I would like to give a brief overview on how to build some of these core data structures using Voila, and I'll also be explaining terminology as we go through that. So the first thing that you might be asking is, well, how can I use Voila? Well, the easiest way actually is you just go to the Maven repository and then you download it from that, the jar files, which is already pre-compiled. So you don't have to do that yourself. So you just go there, search for the con.ibm.voila, and you will be able to find all the packages, all the jar files that Walla has released. You can also definitely clone the repository for Walla and then use Gradle to build from scratch. It's really up to you, but probably you would prefer to use the precompiled binaries. So here I have an example of actually using those precompiled binaries. So I set up a Maven project. So I have my pom.xml file in here, and I import as dependencies all the Walla dependencies. So here it's, I don't know if you can see very well, but I have the Walla core, so you need to import that jar to your project. And then some utilities as well. So this utility component in here is where you would see the graph library, all these algorithms, it's in there. Then you need to also import cast, which is the common AST library, strike as well, and so on. So you import all of those libraries to your project. And then you can specify the version as well. So for example, here I'm using the Walla version of 1.5.7. By the way, this POM file is also released on the tutorial GitHub repo. Now, once you have that, you would actually like to use Walla to do some sort of analysis. So the first thing you have to do when you want to use Walla for any sort of static analysis is to define an analysis scope. What is that? So the idea of an analysis scope is really to specify, well, what project you would like to analyze, what is your system under test. So for example, you can specify what is the folder for the source files you would like to analyze, or the bytecode for it, for example, if it's Java. And you also specify the scope of these functions or classes. So you can have classes that are application scope, extension, primordial, and synthetic. What is the difference between one and the other? So classes that are application scope are basically the classes that it's in your application. So for example, let's say I have a Java program and I have only one class, my hello class, that's an application class. So once I set up the analysis scope, I say, hey, I have a jar file in here. All the classes inside the jar file are supposed to be on the application scope. Now, let's say that I have this my system, my jar file, and let's say that jar file is using the library from Google, the CSV parsing library. Those libraries, you can actually say these are extension scope. So the extension scope is exactly to denote classes that are coming from external libraries that you are importing on your system of test. So that's extension scope. Then we have primordial. What is primordial? Are basically the built-in Java classes. So for example, string, array list, these are all classes are on the primordial scope. And synthetic are basically classes created by Walla to mimic, and you can correct me if I'm wrong, to mimic the behavior of class loading. For example, when you have to invoke the static blocks of classes. So this is modeled by Walla, and this is created by creating synthetic classes. So these are reserved scope that Walla uses to denote those modeling behavior.
So one thing I can just quickly add is that the synthetic class that it's part of Walla's general ideology that everything should be arbitrarily customizable as much as possible in every possible way. So historically, one use of Walla was analyzing enterprise Java code for IBM, and that uses libraries like J2EE Java, the enterprise edition, things like that. And that is a huge mess of mostly dynamically generated code. Although that large mess of code is actually defined by some much simpler semantics, and synthetic was used to create from the XML definitions from J2EE was to create synthetic types that represented that semantics. And that's where it started. And we use it in various ways, just generate whatever. And if you were building an analysis and you thought, okay, I have this library that I care about some aspect of its behavior, but I don't care too much about all the source code, and plus there's way too much source code, and it's reflective of all horrible things, which these libraries tend to be. You could then model, the synthetic loader would be a convenient way for you to model sort of fairly arbitrary behavior. That's what it's for.
Exactly. And so not only you specify your source files and the scope that they are, you also have to specify, exclusion files. So what is exclusion files? Well, when you use Walla, yes? Sorry.
I have a question about the primordial class. So it's the built-in classes, or it also contains the classes defined by the application?
So it's meant to represent the classes built in the Java language. Well, not only Java, but your whatever language that you're using, right? So for example, the primordial is supposed to be for classes such as Java length string, array list, and so on. But of course, when I do the live demonstration, you can see, I can definitely actually specify any scope that you want. So if you want to define everything as application, that is fine. However, in reality, it's better for you to differentiate those scopes so that you can do filtering if you want. I want to analyze application loads, so you can do that. But at the end of the day, the framework will do whatever you specify.
Another thing to keep in mind is that the way these loaders are set up to some extent mimics the actual semantics of JVM execution. So the systems does start with a primordial loader that loads the initial parts of the runtime system and whatever else is in java.star typically. And then it creates another class loader for the application code. Now, Java programs can do all kinds of complex things with class loaders. So we're only modeling that relatively basic start of it. Although, especially if you're doing the synthetic loaders, you can invent other class loaders as well if you like. But this is usually enough for most Java applications. That I'm sure Eclipse does very fancy things with class loaders. We do not really support that. But for most somewhat normal Java applications, this split of class loaders captures the semantics you need.
And then the other part is exclusion files. And when you use Walla, you're using Walla to do whole program analysis. So when you analyze your code, you're not only analyzing that code, that application code, but you're also analyzing all the libraries around it. So for example, when you build a call graph, you don't get only one. Let's say if you have one class, you don't get just nodes that are in that class. You're going to get nodes from all the classes in the Java library. So here, the idea of the exclusion files is to specify what classes that you do not care, or packages that you do not care in your analysis, so that when Walla is creating call graphs or any system dependence graph out of it, those classes, they get ignored. So the exclusion file is basically a text file that looks like a bunch of lines and has regular expressions. So here, for example, I have an exclusion file that says, hey, I do not care about classes that are inside the Java AWT package, for example. And if you want to see how an exclusion file looks like, the Walla, the repository Walla provides an example of an exclusion file. So you can use that as your baseline, as your starting point, and customize as you wish, of course. So I would like to actually do a live demonstration on how to create an analysis scope. So I'll actually switch to my IntelliJ IDEA. So 1 second in here. So here I have an empty class. I don't have anything written. Let me see if is the font visible enough? Should I? Good. So here, so as I mentioned before, this is a Maven project. So I already have Walla imported as dependencies in here. So that's set up already. So now I'm able to use the Walla classes just fine. So what I want to do in here is to create my analysis scope. Okay. So for that, you can use a utility method, which is a static method from this class called create Java analysis scope. That's going to create for you an empty analysis scope. It's going to do some initialization for, as you mentioned before, initialize the class loader things to model that behavior, and it's going to be empty. Now, what you need to do is you need to start adding, specifying what is the path to the jar file you'd like to test, you'd like to analyze. Yes?
Oh, sorry, just a question about the synthetic scopes.
Mm-hmm.
So that makes sense in the context of class loaders with Java, but you also support other languages.
Yeah.
So, is there a reason to use the synthetic scopes in like JavaScript when analyzing JavaScript or Python, or no?
So the synthetic loader in JavaScript.
No. So you have these synthetic scopes and extension scopes to represent. So you mentioned they represent class loaders. So, but does it make sense to use synthetic scopes for JavaScript or Python projects when you?
Typically, those languages don't really have that concept. Although there's, in general, the synthetic loader is something that is used all over the place, right, for modeling things. And
so have you found any kind of uses of like unorthodox uses of the synthetic scope in projects that don't have class loaders? So, Python or Java?
We haven't actually done it yet. One place we're thinking of is in these sort of these JavaScript libraries that are mostly about importing stuff, those might be modeled like this way, although we have not actually done that yet. I see.
Thank you. So then, now I created an empty scope. Now the thing I have to do is I need to specify the Java file that I would like to analyze. So here, for example, I already pre-compiled a very simple example here. So I have a source code. It doesn't have anything fancy. It just has an if condition here. If the first argument passed to the program is even, it's going to instantiate an object from the circle type. Otherwise, it's going to be a rectangle, and it's going to later invoke the draw method. So it's a very simple program. There is nothing too fancy on it. Now, what I will do is I have that program already compiled in a jar file here. So what I'll do is I'll use a class called analysis scope reader. And that class provides a utility method called, and I'll move out of the way, add class path to scope. So here, as you can see, these are the parameters that this method takes in. So basically a path to your jar file, then the analysis scope that you'd like to add, that class path information, and what is the type of scope, if it is primordial, application, extension, or synthetic. So here, for example, I would like to say, hey, I would like to analyze my file called example1, which is inside src, main, resources, and then example1.jar. So that's the path to my jar file. And let me just, I have some zoom stuff in here. So I'm like, let me minimize this so it gets out of the way, sorry. So I have that, and I want to add that to my scope object, which is this one right here. And this should be on the application scope. Okay. So I'm basically saying, hey, I would like to analyze this jar file, and all the classes defined on that jar file should be an application scope. Now, another thing I have to specify as well is my runtime environment, my Java runtime environment. So I already have in here like the runtime, the jar file for the runtime for the Java version 17 here, the JDK version 17. So basically what I'll do is I'll just provide the path to it here. So 17.0.1/ and then runtime.jar. And here now I'll say, well, this is actually a primordial scope. So all the classes on that jar file is actually primordial scope. The advantage of actually doing that is that now you can specify, you can, for example, have multiple Java versions. You have the jar for it, and then you can manually specify which Java version you would like to use to analyze your program. So that's very useful. So it's very customizable, and then you can use in any way you wish. Now, the last piece that is missing is the exclusion file, right? Because I just specify my classes. I would like now specify the classes that I do not care about. So for that, I use the method called set exclusion. And as you can see here, it takes us in as parameter set of classes. In that case, because I want to actually specify that from a file, I'm going to use the concrete implementation called file of classes. And as you can see here, this file of classes takes as parameter an input stream. So it's an input stream to the exclusion file that you have. So in that case, I'm going to create a file input stream. And that file input stream is the file that I already have in here. See, right here. So I have the file. So it's also located on my resource folder. So I'll just copy this string right here. But the name is Java 60 regression exclusions.txt. Okay. And of course, this method is going to throw some exceptions. So I'll just pass that exception up for now. Not a good practice, but this is just a quick demonstration. All right, so now I'll just print the scope so that you can see in here. So I'm not going to be doing anything fancy so far. So I just created the scope in here. So I set up everything. And noticing here, I just printed it. And as you can see, everything got set up correctly. So I have a jar file module, which is my runtime.jar file in the primordial scope. I don't have anything on my extension scope because I have not defined it. But then I now have on my application scope, I have example1.jar, and then a list of exclusions in here, which is all those regular expressions. that I had on my exclusion function. Any questions so far? So that's the first step for you to actually start using Walla. You specify an analysis scope. Now, let me go back to presentation. When it comes to analyzing object-oriented programs, you have to specify something happening here. Okay, now it's back. You have to specify a class hierarchy, because if it is an object-oriented program, you have to know what are the classes in there, what are their methods, and who they implement, what are their implemented interface and extended classes. So for that, you need to build the class hierarchy. So Java already provides utility classes for you to do that. So what you want to create in the end is an I class hierarchy, which is a data structure that you can use to create that hierarchy for you. So what you can use is you can use the class called class hierarchy factory, and that has a method called make. So you pass to it the analysis scope, which already specified your system under test. So once you do that, you do class hierarchy factory dot make, you pass the scope, and that method returns you the class hierarchy information. So using that data structure, you can have access to all the classes in your program, their scope, if it is application, primordial, and so on. And you can also see what interfaces each class is implementing and their super types as well. Okay. And then you can also see, for example, these are the methods declared in the class. These are the methods that are inherited by the super classes. So this is a very useful data structure that you need to create. Now, when it comes to doing static analysis, the core data structure is call graph, right? So, because if you're not doing sort of static analysis, more likely you'd like to do some sort of interprocedural analysis. So you would like to extract facts that cross multiple boundaries in terms of methods. So for that, you need to build a call graph, which is basically a directed graph that tells calling relationships between methods or functions, if it is an imperative program. So the idea of a call graph is that the call graph have entry points, right? So the entry points are basically the methods in your program that starts the execution. So for example, in Java programs, that's your main method. But of course, as you will see soon, you can specify the entry points in any way you wish. So by default, Walla uses the main method as the entry point of your program, but you can definitely specify, hey, this other method right here from this class should also be treated as entry point. So that's going to be the root, quotes and quotes, of your call graph. And then from there, Walla can use multiple algorithms to infer what methods are invoked by this method right here, by your entry points. So it's an iterative process to build the call graph. And of course, nodes on those call graph, they will also have a scope. It depends on what is the class that method belongs to. So you can have nodes that are application nodes, you can have nodes that are primordial nodes, and so on, and also syntax. Now, Walla provides some algorithms already built in for you. It's already supported by Walla, so I'll be explaining 3 of them. So I'll be explaining class hierarchy analysis, rapid type analysis, and MCFA. And Walla also provides KLCFA. One interesting thing about Walla is that you can, because everything is provided in terms of interfaces and abstract classes, you can also create your own algorithms to build call graphs. So let's start talking about the first algorithm, which is class hierarchy analysis. So this is a very basic algorithm. It's very cheap to compute. And the idea is that you would like to rely on class hierarchy information to build a call graph. So for example, here, let's say I have here an interface called shape, and that interface defines a method called draw. Then I have 3 concrete classes, triangle, rectangle, and circle, that implements that interface. So each of those classes provide a concrete implementation for the draw method. And of course, those concrete classes, they also extend the object class because that's how Java works. Now let's say that I have in my program, I have a shape object, type S, type the static type is shape. And then sometime in the program, I do s.draw. If I were to ask you, what is the actual dispatch of that method? You probably would be answering me that, well, the actual dispatch at runtime would be based on the runtime type for S. So if S was initialized to equals new circle, so you know for sure that the draw method would be the draw method from the circle class. But right now we don't know that. Maybe this information here is coming from outside, coming from somewhere else that you cannot really infer statically. So when it comes to answering that question, what is the dispatch? this algorithm, the class hierarchy analysis, simply rely on static type information. So it's a type-based reference analysis that once you have a situation like that you have a polymorphic call, it's going to infer based on class hierarchy information. So basically what it does is that it computes the cone of a type. So cone, what is a cone of a type? It's basically the subtree in which that type is the root. So basically, for example, the cone of shape would be triangle, rectangle, and circle, right? So that's how this algorithm works. So in that case, what you would say is that, well, if I have this object here of type S, of type shape, and if I'm invoking the method draw, the actual dispatch could be either triangle, rectangle, or circle, because the three classes, they are providing a concrete implementation for that interface. So that's how it works. And it's very cheap to compute because it only relies on a pre-computed information, which is the class hierarchy. So you can do that in one pass. And of course, you have to do the cone. So it's kind of linear on time. So as an example in here, I have the same class hierarchy here. So I have shape, I have triangle, rectangle, and circle. And if you notice in here, that's the first program that I had before. I have an if condition. If the first argument of my program is even, the runtime type of S is a circle, otherwise it's a rectangle. And then later on, I do dot draw. If I were to ask you to manually analyze this code, you would be able to tell me, well, the true call graph for it is that when I do s.draw, the draw method could either be a circle or a rectangle. Because if you look at here, this is the runtime types. But remember, when it comes to class hierarchy analysis, it does not look on the object types at runtime. It does not look at the object instantiation. Instead, it just looks at the static type and how it looks like in the class hierarchy. So when you actually build the call graph using this algorithm, you would see that the call graph would look exactly like this. So you'd have your main method, and then you would see that the main method invokes the constructors for circle and rectangle, right? And once you have dot draw here, the possible dispatch for that invocation could be either circle.draw, rectangle.draw, or triangle.draw. See? Because again, when I compute the cone of the type shape, I have that three possible classes. Okay. Now you might be asking, well, cool. So I understood the algorithm, how I can actually compute this call graph using Lala. So for you to actually do that, let's say I created a method in here called build call graph that takes my analysis scope that I previously built and takes the class hierarchy as well. They are already built, right? So all I have to do is there is a class in Lala called call graph, and that takes as arguments the class hierarchy that you already built, and a parameter here that can be true or false. So if it is true, it's going to be the call graph that only contains nodes from the application itself. If you put it false, it's going to be a call graph that has everything, including primordial class and so on. Okay. So here, to keep the call graph small, I just say it's true. I only want application nodes. Now, remember that I said that call graphs, they have to have entry points because that's where you start constructing the call graph. So you have to specify every time you create a call graph using Lala, what are the entry points of your application? And it's basically a list of entry points. Lala provides a utility method for you to compute entry points based on main methods. So if you only care the static main method, you can use this utility method that's going to go over the class hierarchy and the scope, and it will give to you a list of entry points on your program that basically are your main methods. So every time it finds a main method in your jar file, that's going to be part of that collection. Okay. And then now I initialize my call graph and do dot init, and these are the entry points of my call graph. Right. So with that, I'm going to create a shell call graph, and that has only applications. Okay. Any questions so far? So this is a very simple algorithm, and of course, in the real life, it's more likely you will not be using it. But I would still like to talk about the kind of a variation of it, which is rapid type analysis. So it's very similar to class hierarchy analysis when it comes to building call graph, but it does an extra step. What is this extra step? So it relies not only on the cone information, so on the data types, on the static types, but it also looks at the type that were actually used in the code. It's actually the types that were actually instantiated in the code. So if we go back again to the example that I had before, we can see that shape has 3 concrete classes: triangle, rectangle, and circle. However, we can see that by looking at this code, triangle was never instantiated. So triangle is a class that exists. It's available in my class path. However, it was never used. So when I have s.draw, what this algorithm will do is that it will still rely on class information, class hierarchy information to compute the possible dispatch, but will exclude from it those types that were not actually used in the code. So if you look in here, the dispatch for s.draw would only be circle and rectangle. The reason being because triangle was never associated. Okay. Any questions so far? Now, yes?
We should probably point out one thing, that this is actually the first place we're going to see what's the general difficulty in code graph construction. She said, and rightly so, that RTA looks at classes that are instantiated, which sounds simple enough. But what do we mean by instantiated? Typically, what we mean is created by explicit new statements. But what about weird reflective things that do a bunch of string processing and then make something? The chances are analysis is not going to understand that those are instantiated. In a way, this is the kind of the first simple example where you start to see the trade-off in, as you try to make your analysis algorithms more precise, actually making them correct becomes harder and harder. So that's just, and you will see, if you start build more precise algorithms, you will start to see things like that.
Exactly. So now let's say I actually want to build an RTA call graph using Lua. You can actually doing that by, now it's going to start getting a little bit more complicated. So you need to create an analysis option in here. And using that analysis option object, you set what is the entry points of your call graph. And again, I'm using the main entry points of my project to be my entry points. This is an analysis cache object, which is used just for the sake of performance, so just to cache some of the results of the analysis. Now I need to use a call graph builder, an RTA builder. So there is a utility method from the util class that you do util.makeRTA-builder. You pass the analysis option, the analysis cache, the class hierarchy, and the scope, and it gives back to you a call graph builder. Okay, so it's a call graph builder that you can use to build call graphs. Now, for you to actually build the call graph, you have to invoke the method make call graph on top of the call graph builder. Okay, and of course, have to specify the analysis options here. And the second parameter here that I specified as null is a monitor. So it's basically an object that you can use that is a callback, is an interface that you can use to just basically track what is the progress of your call graph construction. Here, because I do not care about monitoring the status of my call graph process, I'll just specify it. Okay. Any questions? All good? Yes?
A couple of points you mentioned that the analysis relies on sort of types, uses types, right? But the other languages like Python, JavaScript don't support type. So is there a way of, can you, so obviously these analyses don't apply there because I guess there might not be a similar notion of class hierarchy. But if you don't have like annotated with code with types, can you still use some of these techniques? Or
so the two things. First, it's true that some languages like JavaScript, traditional JavaScript, not TypeScript, have really no notion of types at all. At which point trying to talk about types is a little bit. Python, on the other hand, does have notions of types. It's dynamic. They don't have static types, but it's still the case that you could ask questions like what types are actually instantiated in this program. So there are some, to some extent, things like an RTA could make sense in Python. And more generally, if you could imagine taking something like TypeScript, you could imagine trying to take the types on faith. That's, I mean, if they're not enforced, right? TypeScript is entirely comments, really, but you could choose to pay attention to them. Yeah. So in general, the less statically typed your language is, the less you can typically do to exploit this sort of information. So in Java, when you're doing analysis, you typically look at you have a declared type of a variable, if analysis gets imprecise and returns something that doesn't make sense, you can exclude it on the grounds that you know that that must be an analysis of precision. Whereas in something like Python, you don't really have that ability. You also have things like check cast operations that you can do in other languages as well. But in general, the more dynamic the language, the less you can do. But
I see. Yeah.
we can map things in Python to types. As I said, JavaScript's a bit difficult, but it's more of a continuum than it only works for Java.
Right. Yeah, I guess it would be more imprecise.
Yeah.
So I have a question. I don't see the reason to use class hierarchy analysis because does the RTA not cover every case that the class hierarchy covers?
So there are two options. One is that even the RTA class and algorithm does have to scan all of the source code, all of the bytecode of the source code, in order to see what types are explicitly created. And the class hierarchy analysis does not do that. So that might be one trade-off, depending on exactly what question you're trying to ask. The other reason for carrying is, as I was saying, talking about soundness, that the more we try to exploit things like what gets created, the more important it is that our analysis of it actually be correct. In a sense, class hierarchy analysis is very safe, very conservative. It embodies Java semantics in the sense that every type that implements this interface could be here. And that is, from the language semantics, that's clearly, that is an over approximation. Once as we start to shrink it, the analysis gets more precise usually. The analysis, often it gets faster just because it's building smaller data structures. But there is this trade-off where you're never quite sure that you didn't miss something.
So in RT, it is possible that we are missing another option, right? So my question is that assume that it was more dynamic than the example that we showed. Would it miss like the call the triangle?
No. So the kind of things it misses, this is where the whole, I don't know if you've heard of the notion of soundiness, the idea that my call graph is meant to be as correct as is reasonable. The RTA is definitely in that category. So to think of this, for example, in many versions of JVM standard libraries, the whole notion of certain kinds of character converters, the way it supports different languages, and it actually uses the names of languages and things to construct the type name of a converter and then instantiate that. Now, class hierarchy analysis won't be fooled by that because it will just see all of these character converters and will assume they're instantiated. It's very unlikely that RTA is going to discover that they are in fact instantiated in the class loading process of the standard library. So it will miss. Probably you don't care, but maybe you do. But in normal user code, you would not expect to see that kind of problem. Although increasingly in framework-based code, which makes more and more use of reflection, it becomes more and more rich.
Any other questions? All right, so these two algorithms that I mentioned before, these are context-insensitive call graph construction algorithms. So what does it mean for an algorithm to be context-insensitive? The idea that what happens is that those algorithms, they conflate, quotes and quotes, multiple call sites in the call graph. So let's try to understand with an example. So here I have a main method here, and depending on if the argument is even or not, I'm going to invoke either the static method called draw circle or draw rectangle. And each of them takes as input as a parameter a shape. So it's the static type is shape. And then inside of those two methods, I do dot draw of whatever argument you pass. So if you look at the call graphs that are built when you use SHA and when you use RTA, you can see that these call sites, even though they are different call sites, the dispatch got the same. So you can see that the draw rectangle and draw circle, they're effectively invoking the same node in the call graph. You can see here, and you can also see here. So they are conflated. There is no distinction to the fact that yes, they are invoking the same method, .drop, but they are different call sites. There is no distinction. That's a context-insensitive call graph. On the other hand, how about we try to make this context-sensitive such that our call graph no longer conflates these different call sites? So how can we do that? So there are multiple algorithms to achieve context sensitivity, and I'll be talking about one of them, which is the one KCFA or NCFA. But the idea here of a context-sensitive call graph in general is that now, when you have a context-sensitive call graph, a node in your graph will be a pair, in which one part of the pair is a method, and the other part is a context. So that means that you can have different nodes on your call graph that represents the same method, but has a different context. And the idea of the context is exactly to abstract the programming state of that call site. Okay, and then of course, depending on how you specify, how you abstract that context, that's when your analysis becomes field sensitive, heap sensitive, and so on. Call site sensitive, object sensitive, and all of that. So as I mentioned before, now in your call graph, you'd have methods and a given context. And when it comes to entry points, your context is more likely empty or a dummy context because there is no programming state yet, right? Because your program has not started executing. So, and of course, depending on how you specify, oops, sorry, I lost myself in here. Oops. So a bit slow. And of course, depending on how you define your context, your analysis becomes more or less sensitive, more or less precise, and also more or less costly. So I'd like to talk about one of those context-sensitive algorithms, which is the KCFA, which is control flow analysis. So the idea of this algorithm here is that I'm going to define context based on call site strings, so call strings. So the context is now based on who called that method. It's going to be an array of callees. And the idea is that now you do method cloning, so you can have the same method in different nodes on your call graph. And you also do points to analysis. So you also look at what are the possible variables that this pointer can point to, depending on the allocation. So let's actually take an example of a code so that you can understand this algorithm. So here, for example, I have a main method, and then I'm reading a string from the user. So I'm calling the next method from the scanner class to get a string. And I'm invoking the static method alpha twice in here. So alpha, and I'm passing the actual value passed by the user. And then alpha, and I use the string height. So notice these are two different call sites, call site number 2, call site number 3, right? And then here I have alpha and beta. And then in the alpha, I invoke beta here, that at call site 5, I invoke beta. And then beta returns a value here, which is 8. So if I were to build this call graph, we're using one CFA, so I only keep track of the immediate caller. So just one element, one caller. So what I would have in here is that I would have the main method. Of course, it invokes the next method in here at the call site 1. That's fine. Then I invoke the alpha method here. And even though it's the same method, I'm going to distinguish one and the other, because one is at the call site number 2, the other one is at call site number 3. Now, if I look at the implementation of the alpha method, it invokes the beta method. In that case, the call site, the context for it will be C5, because remember, my context is only 1, it's bounded to 1, so I only keep track of the immediate call site. So in that case, it's C5. So notice that at this call site, the dispatch got conflicted. Right? Now, if I were to use 2 CFA, now because I'll be able to actually keep track of my call sites twice, so I have the bounded 2, now I'll be able to distinguish those 2 call sites. You can keep increasing the bound of that algorithm, but previous research has shown that increasing more than 2 does not add much precision, just makes the analysis more costly. So people typically use 1 or 2 when they build the call graphs. Okay. Now, how can we actually build the call graph using one? But before I talk about that, before I actually show you how you can build the call graph, I'd like to talk about Wallace intermediate representation, which is one of the core data structures in Walla, and it's probably one data structure that you'll be using a lot when you're using your analysis. So the first thing that you have to understand is that every node on your call graph has this intermediate representation. So this intermediate representation is an object from the IR type. So it's an IR type. And it has instructions and control flow graph. So using the IR of a method, when you do node.getIR, so node from your call graph and you do getIR, you have access to all the instructions of that method and also control flow graph. Now, one thing that I would like to mention is that the instructions in your method, they are actually representing single static assignment form, in SSA form. So if you have taken a compilers class before, you probably remember that the idea of that form is that every variable in your program gets assigned only once. So if I have the program that I had before, in which I had an if condition and S, the runtime type of S depends on the actual argument in here if it's even or not. So I'm actually writing the value for S twice. So now when I actually try to convert that code to SSA form, what I will be doing now is that I'll be creating fake labels. And what Voila does, it's the labeling is basically variable numbers. So it starts at 1, and 1 is going to be the parameter of your method in case of static methods. If it's not a static method, it's going to be the this pointer. So for example, if I try to rewrite this method in here in SSA form, I'll have v1. So instead of r, this is v1. And then here what I'm trying to do is I'm trying to access the argument at position 0. So I'll first declare a variable, for example, v3 is equals to 0. And then v4 is equals to the accessing the element 0 of the array v1. And then the output, the computed value for parse int will be assigned to another variable, v6, for example. Then v7 is the value number 2. v8 is the computation, the reminder computation of v6 and v7, and so on. Now, one thing I'd like to highlight in here is that at this line right here, I'm trying to do s.draw, and s could be either this s in here from the if condition, from the if branch, from the true branch, or it could be the s from the false branch. So remember, in SSA form, when you have possibilities, this is represented with a fee instruction. So you have a fee instruction like this that would say, hey, this variable in here, that's going to invoke the method draw, the variable number 13, could either be the value from v11, which is the result of the true branch, or v9, which is the result of the false branch. So when you do .get IR from Voila, you have all these instructions exactly represented like this in SSA form. You can, there is a way that you can also map back those variable numbers back to the actual variable number. You can also do that. And as you can see here, these instructions, they are organized in basic blocks. And that has to do with the control flow graph of your method. So a control flow graph is also a graph in which the nodes are basic blocks, which is basically a set of instructions that will execute together without any jumps. And the edges represents the flow from one instruction from one block to another. So it basically represents the flow of that method. And the control flow graph has two extra nodes, which is the entry block, the beginning, where it starts, and the exit block, which is where it ends. So if you were to look at the control flow graph of the method that I had before, I'll have the basic block number 0, which is my method entry, and the basic block number 13, which is the exit. And as you can see here, so I'll start the execution. So I have my first instruction, which is loading the array, which is loading this array here, this element, the element 0 from args to a variable. Then the next one is actually computing parse int of that element, and then doing the computation of this reminder here. Now I do have a jump, so I can go false or true. So the Voila will give this control flow graph to you exactly like this. So a bunch of basic blocks that you can iterate over, so such that you can get the instructions. Okay, any questions so far? Now,
we should probably just note that one thing you don't see on those graphs is all of the edges that you think must exist to handle exceptions. And typically most instructions in Java can throw exceptions in one sort and another, but by and large you don't catch. So there are sort of implicit edges to the exit for exceptional control flow, unless you do explicitly catch it, in which case those get represented as edges to exception handling.
And before I forget, I forgot to include on these slides in here. So I'm quickly show how you can actually view that NCFA graph. So here, if I go back to my IDE, so I can use the utility method called util.make NCFA builder, as you can see here. And as you can see, these are the parameters of it. So you can specify the N. So for example, 1, 2, that's going to be your N of your algorithm, the analysis option, the analysis cache, the class hierarchy, and the analysis scope. So for example, I want to build the one CFA. So I'm going to say this is 1. I'm going to create my analysis option in here. Options. Here it's empty. So I'm going to set the entry points in here, make main entry points, scope. So I'm going to specify those options. Then an analysis cache in here. So I'm going to use this one. My class hierarchy that I computed before. So use that in here. Factory. So I create my class hierarchy. And the last argument, last one is my scope. So remember, this method in here will return to me a builder, right? A call graph builder. So now what I need to do is actually to invoke the method make call graph to actually build the call graph. So that make call graph will actually return a call graph object that is actually the call graph using one CFA. Any questions? Yes? Exactly. So if you want to get the control flow graph of a method, you need to build the call graph so that you can get the IR of the method, and then from there you can get the control flow graph. Right. There is a way that we can also just build the control flow graph, if I recall correctly. There is an IR factory, which can do make IR, right?
Yes, so under the covers, the call graph construction is using the IR factory, and it is possible to use the IR factory directly. If you simply want to say, here's my class, okay, I just want the IR of this method, and I'm not interested in anything like who called it or what, I just want that method. You can use the IR factory directly.
Yep, exactly. I don't remember exactly the method. I think it was a make something. I don't remember.
IR factory, the default IR factory.
Yes, make IR. See, make IR. Now, of course, you have to specify the method, and you also have to specify a context. And in that case, what you can do is you can use actually context everywhere, which is a dummy context. So it's a kind of a placeholder context. So you do make IR and use as context this placeholder right here. That way you have the IR, and then from that you can get the control flow graph.
And you should be able to, if you do it on the IR factory, if you just IR factory dot, it should be able to give you a method called default IR factory.
Yep.
It gives you a factory back, and then you can use that to make IRs. And as Joanna said, you should just use everywhere for the context in that case, because context only makes sense in the context of a scope.
Yeah, and in fact, that default IR factory also has a utility method to make just the control flow graph. Cool. So yeah, Awala is a quite powerful framework. Any other questions so far? Now, if you're noticing here, just gonna print the call graph, get number of nodes. Just gonna throw all these exceptions. What is the problem here? Oh, I have to pass the class hierarchy. Sorry, what's the problem here? Now, if I execute this code in here, unless I have messed up, so I printed the scope, it's building the call graph. As you can see, it does take some time to build, because even though it's a very small program, remember that in the end, you're not only analyzing your program, but also all the Java classes. Sorry, I'm allergic today. Forgot to take my allergy pill.
8,461. Most of that is weird stuff. As soon as you do object.init, it starts to dream up static initializers of system classes, and it quickly sucks in all kinds of random stuff.
Yeah.
So you get thousands of things just for waking up and falling. And that's not really the fault of the analysis. If you run Java, dynamically, and you would tell it to dump all the classes and methods it's loading, waking up in the morning again generates thousands and thousands of methods, and some services is accurate.
Yeah. Now, one interesting thing that I kind of use a lot when I'm kind of debugging my analysis is that Walla has a class called Walla Viewer, right here. So that Walla Viewer, you pass to it a call graph and a pointer analysis, which is an object that basically holds the points to sets information. So once you do that, it's going to open a very nice window that shows the call graph kind of in a tree-like way. So you can get the pointer analysis from the builder class here. So once I do new Walla Viewer, that should create that window. Also, the call graph is used. So just give it some time, and we can actually see that on that UI, which looks kind of nice. There you go. So it's opening that Swing application a little bit. So as you can see here, there is a bunch of nodes that got created. And one interesting thing here is that actually your call graph has a root node, and that's not your entry point. It's actually a fake root node, as you can see, and it's a synthetic node. So the idea here is that to be kind of the glue connecting all the entry points of your program, because if your program has multiple entry points, it becomes a forest, right, instead of a graph. So the idea of this fake root method is exactly to be this glue connecting everyone. And here, for example, I have my main method here, and then you can see the node, the main node, and all the instructions inside that method. And then you can see all the invocations that occurs inside that method. So for example, an invocation to the parseInt method, which is static, and also to the draw, the constructors of the circle and rectangle, and also to the draw method. And if we look at the draw method in here, as you can see here, there are two possible dispatches, one from the circle class and another one from the rectangle class. So the wall of here is kind of a nice way for you to see all this information. And as you can see, once you click on a node, you can also quickly see the control flow graph of that node right here. So you can see the control flow graph and also the instructions in here with the basic blocks information. Any other questions? I think this is a good time maybe to take a break because it's 10:22. What do you think? Or should we?
And just one thing to note, you notice in there, you see finalize. It's like I don't recall calling finalize anywhere.
Mm-hmm.
And anyway, why is it a root? Why is it called from the fake root? And the reason is that the finalize, from the point of view of the user's program, is invoked asynchronously by the garbage collector. It is not actually called from the user code, but it's definitely code that gets executed, and so it gets put in there.
And a similar comment as well to the class init, this one right here, which is exactly to mimic the behavior of initializing the static blocks of classes. Because when you have a static blocks of your class in your class, it's that block gets executed when the class is loaded. So the idea of this method here is exactly to invoke these static blocks, so that execution is there and you can see in your analysis. But of course, it's out of order because it just says that it's going to execute, but does not say when. Any questions? Yes?
So, I wanted to ask, you said that it takes long to generate these classes of Java. Is it possible to have like an edit mode where you load all of those, and because the underlying code doesn't change much, you're changing the analysis, and while you make the analysis, and you want to test if your analysis is financing the component. And would it be possible to load everything, and then just when you change the analysis, it just runs the analysis again instead of creating the objects in the mind?
So what do you want? So what do you want to create again? What do you want to reuse? I mean, things like the analysis scope and the class hierarchy and that sort of thing.
So yeah, I mean, when you load all the Java objects and everything, but so let's say everything about the code under analysis is stable, and I don't change that.
So you'll have something like, say, the class hierarchy object in the IR, and so will be constant, will be fixed.
Yes, okay. And then I implement my analysis and run once, then everything gets completed. And the second time that I run the analysis, it doesn't recompute the IR.
definitely you can do that. So let's just go back to one of your examples of building the IR.
Oh, beauty here.
Yeah, one of the examples of building a call graph, like the MCFA building.
Oh, yeah.
So can you bring all of that code onto the screen at once? So if you look at what we're doing.
Sorry, you want that code, this code right here?
So if you look at what we're doing, you build a class right here, it's setting up the analysis script here. And then down here, it builds a call graph. But this depends on that, but not the other way around. If we wanted to, we could build another call graph here, which uses a different building algorithm and reuse the same scope and cache and things. And in general, yes, even the analysis cache computing the IR would be reused, assuming that the cache is going to keep track of the IR or a method and a context. So if you in a subsequent call graph you use more contexts, you will need new IRs because you told them. If you use the same context, or if a bunch of people used everywhere as the context, even the IR would be reused. Yes.
So I think we can take a break now and then we can return at 11, right? I'll stop sharing. Welcome back, everyone. I'm gonna continue now talking about, we talked about call graphs. Now let's start talking about program dependence graphs and system dependence graphs. So right now we look at call graphs, and call graphs are a very useful data structure. We have seen that before. It's important for us to do inter-procedure analysis, so we need a call graph. However, call graph express facts at the method level. You are not able, for example, to see how an instruction depends on the other in terms of data and flow. So that's why, just by looking at the call graph, you don't know exactly how the method is going to execute and how data flows from one place to another. That's why, for that reason, we have other types of data structures that can give you that information. So one data structure I would like to talk about is program dependence graphs. So program dependence graphs are also directed graphs in which the nodes are statements in your program, and the edges, they can either represent a data dependency or a control dependency. So for example, here I have 4 statements, and as you can see here, the statement number 2 is doing D equals A plus 1. If you look at that statement is using the variable A, and the variable A was defined on statement number 1. So A equals B plus C plus 12, that value is passed to statement number 2. So that means there is a data dependency from statement number 1 to statement number 2. Similarly, statement number 3 does an if condition on the value of A. So that is also data dependency from statement number 1 to also statement number 3. Now, if we look at this code snippet, we can see that this print statement stays positive, only executes if the if condition here is true. So basically, the statement number 3 controls the execution of the statement number 4. So for that reason, there is a control dependency from S number 3 to S number 4. So the program dependence graph captures exactly those type of dependencies, from data dependencies and control dependencies. So here's a very simple example on how a program dependence graph would look for this same method here. So for example, a program dependence graph always has a method entry and a method exit to represent the beginning and the end of that method. Then here we have the variable I, and that variable I is being used on the while loop, the beginning of the while loop. It's also used on this statement here that increments the value. And notice that the increment of the value would create a new value for I. So that's why there is a data dependency from here back to the while loop and also on itself. And the while loop controls the execution of the increment in here. So that's why there is a control dependency in here. So program dependency graphs, they are only at method level. So they only tell you facts in terms of data and control dependencies for one method. So that's not enough for you to do a whole analysis of the system. That's why we have system dependence graphs. Because for example, let's say you want to track data flow that's spanning across multiple methods, you need to have information about multiple program dependency graphs. So the idea of a system dependency graph is really just to get these procedural graphs and then connect each other. And the way these are connected to each other is by creating dummy nodes. So these dummy nodes, they represent the actual and formal parameters passed to a method invocation, and also actual and formal return values. So the idea is that you have all these PDGs, and then you connect them by using the arguments and the return value. That's sort of the idea. So here is a very simple example that I still have my while loop that increments the value for I. But now what I do is actually invoke the static method called increment that basically returns the parameter plus 1. So noticing here that I had my program dependency graph as before, right? So that's the program dependency graph for my main method. But now, noticing here that do I equals increment. So I'm invoking the static method increment. So in that case, this controls the execution of the method A3. So this is a program dependency graph for increment. And noticing here that I do pass a value to it. So the actual in is the value for I, and the parameter in, the formal parameter, is X. So I connect that data dependency in here, the return statement. And also there is a return value here. So there is a dummy node to represent the color and the colleague. And there is a data dependency. So noticing here that the system dependency graph for this programming here is basically two program dependency graphs, and they are connected by this dummy node. So that way now I can track how the variable I, for example, flows across the whole program. Now you might be asking yourself, okay, cool, but how do I actually build those data structures using Lala? So for you to do that, and I think I made a mistake in here, so apologies, I clicked on the wrong button. So for you to actually do that, what you need to do is, again, you need to build your call graph, and we have seen all these pieces before, so I'm not going to explain that again. Now, the new part in here is to use the class SDG, which stands for System Dependency Graph. And as you can see here, the parameters that you need to pass to that data structure is the following. So you need to pass the call graph right here. So you need to pass the call graph. You also have to pass your points to set. So basically pointer analysis information, and you get that information from the builder class. Remember that. Now you need to specify how data and control dependency edges should be created. When it comes to data dependencies, you can have, for example, data dependencies through the heap, through also base pointers as well. So you can specify here how you would like to create those data dependencies. So here I'm saying, well, I would like to ignore dependencies that go through the base pointers and through the heap. And when it comes to control dependencies, you have control dependencies created by conditional structures such as if conditions, switch case, while loops, but you can also have control flow dictated by exception. So for example, if I have an if, I have a statement that throws an exception, potentially throws an exception. So the next statement is controlled by my previous statement, because if the previous statement throws an exception, the next statement is not executed. So here at the second parameter, I can basically say, hey, I would not like to track those exceptional edges. So if there is a control edge which is called by exception, I would like to ignore that. But let's say if you would like to include that, you can just say dot. So this is basically how you create a system dependency graph. You pass all the data structures that you created before, and now you specify how you would like to track data and control flow dependencies. Any questions so far? So with that being said, I'd like to pass back to Julian, who that is now going to show how you can use all these data structures to actually do some sort of useful analysis. So, floor is all yours.
Thank you, already, I'm sure you've seen already what Joanna has told you is in fact quite useful in some situations. However, there are one of the things you might be thinking, okay, so I've built the system dependence graph, which is something we're going to use shortly. So what kinds of things do people do with this? What do we do with Wallop? So and I'm going to start with, I'm going to talk about some taint analysis, but before I do that, if you're going to analyze something, you kind of have to have a summary. In this case, we need a program. And I'm going to be using a JavaScript example. The code we've seen so far has mostly been on Java, but things like there are slightly different there. The core graph construction is similar. There are a couple of the sort of utility classes that Joanna showed you for Java. There are similar things for JavaScript, Python, for HTML. And we're going to use JavaScript mostly because I want an example that is code that isn't particularly trivial, but also fits conveniently on a slide. And as a way of basically turning line noise into extremely complex control flow, JavaScript is unsurpassed. In terms of just jamming random complexity in incomprehensible ways into small numbers of characters, is pretty good at that. So let's take a look at what this example does. And we start at a high level. What are we doing here? It's basically a model of something that might have come from a web page. So you see something at the top here called document. Now, if you use JavaScript in HTML, you know about document, and it has a URL, it has a function called write, and this is a model of that, basically. And in fact, document underscore prototype underscore write is in fact a Wala model of that piece of DOM function. So let's just see what this program does. So we have our document, we have a function ID, which what does it do? Nothing. It returns exactly what is given. And then this example ID is a very common example for people who want to talk about things like context sensitivity, because it's very useful, it's very simple. But at the same time, if you do something completely insensitive, you get that. So that's what this is for. And now this is JavaScript. So this is actually a constructor ID, and it has one field called ID, which points to this function ID as well. And that's just a way, that is effectively the way of writing methods in JavaScript. And then we have sub ID, which doesn't do anything, but it's got a prototype, and that is roughly how inheritance sort of kind of is done in JavaScript. And now we do a few things with these things. First, we do this math.random. We just generate a random number, let's go from 0. Then we make a new ID object, and we call its ID method. This is a reflective way of doing call, right? Method function dot call in JavaScript. We call our ID method, you giving it document or URL. Otherwise, we do another math.random, and if that's we do the same thing, we do something with a sub ID. We pass it this funny string, not a URL. You can maybe guess where that's going, but just bear with me for now. And then if neither of those two, we make another sub ID and we pass it document or URL, and then we call document. I mean, then for each of these things, it's returning something, and we write this tag. Now, what does this do? This is going to pass document or URL to ID, which is simply going to return it. So we might sometimes be writing document or URL here to the screen. And probably if you write JavaScript, you've been told not to do that without checking a little bit about the URL and see where people are corrupted, but who knows what it's basically. So, and this is basically, does this code leak vulnerable data? So we're printing to the screen, that's potentially a leak. We are reading document or URL. It turns out that URLs are actually vulnerable because people do all kinds of things like their own state after the anchor tag and things like that. It's all really, really bad, but people can do it. So potentially, we read the URL and we write to the console. It might leak, right? But is there a path? I mean, obviously, if I read into the URL in one place, I do something, and then I write some completely unrelated stuff, that's fine. Is that what's happening, or is there actually a path? So this is what taint, and this is the kind of question that taint analysis is going to answer. So, and that's why this example is as involved as it is. I want multiple paths, and I want it to be not immediately obvious that this happens, and so on. So to try and obviously, this is a human could answer these questions in a couple of minutes by looking at it if they understand the JavaScript semantics. But we want to motivate why you might need analysis here. So so what are we going to do? So we're going to use things like the system dependence graph. And as Joanna explained, the system dependence graph is actually globally keeping track of data and control dependencies in the program. Now, for taint analysis at the moment, just to keep the example simple, we are going to focus on data flow. I mean, you may have heard of things like indirect reads and things like that. control dependence causing security issues, and that can happen, but we're going to ignore that. Even I don't know how to make that fit on a slide. So these red lines essentially represent in data flows. Document.url, here we go. It goes over to return because it's call, id.call, is passes an argument with this to id1.id, which is this guy, which is this guy. So then there's data flow there. That's just one, and then return. It returns back to text because that's where the return value gets assigned. That's what two of those are, and they're all like that. And the thing to note here is this arrow. It's kind of obvious when you look at it, but the semantics involved. First, there's this guy. We have to figure out who he is. ID1, ID. It gets here, comes from here, and then that's this guy. There's a lot going on, and this is what the kind of thing that the system dependence graph and Waller's JavaScript semantics gives you. It basically build this graph for you, and you can just say, okay, where does this go? And even now, is there a path? Of course there is, right? Otherwise, I wouldn't be using this example. But leaving that aside, it's still not entirely obvious, is it? So let's just see.
It's something.
Sorry? Yeah. It's slow.
It's a little bit slow, yeah.
It's slow. Okay, so, and this is what I was saying, we must understand the semantics. These edges, this is the URL that was returned to the function that was stored in a field that was written from another function that returned the value that lived in the house that Jack built, if you get that lesson. Basically, the point is the semantics are fairly complicated, and that's what you get. That's what this graph is giving. You can see these. You'll just get these. We'll just get these lines to reason over. But actually, building those lines is used. As Joanna was saying, call graph builder, control flow, control dependence, and all of those things. And again, going back to what Joanna was talking about with context sensitivity. Look at return here. I'm returning X. Now, as Joanna was saying, if it's context insensitive, then I would have exactly one representation of X in my analysis. And that would have data flow from here, and from here, because all of those get passed ultimately through this guy as a parameter. And I also only have one representation of X. And then, so then what I would see is data flow from one representation of X. I would see data flow that started here, went to the return, and then went somewhere else. But I also see data flow that came from one of these tainted ones to the return, and then back to this guy who's perfectly fine. So we're going to need some context sensitivity there. And what we're going to actually look at is a slightly different way of thinking about context sensitivity that will solve this sort of problem for us as well. So let's start with graph reachability. So as I said before, we have that graph I showed you just seeing. So let's look at the data flow portion of the SDGI as a subset, because there are even more edges than this, but we're not going to worry about that.
Can I ask you a question?
Of course.
Yeah. So in terms of the extensibility of Voila for using these components to define custom analyses, it seems like construction of this of the dependence graphs requires some deep knowledge of the semantics of the language. I mean, it requires some sort of involved encodings of the semantics of the language in terms of how these how the prototypes work, etc. So do you envision people actually writing their own dependence graphs, or is the dependence graph really a component that you can just take from Voila and then you write other stuff?
So mostly we imagine people using them. Now, Joanna showed you arguments for creating it. Do I want to track exception edges? And that's sort of a way of saying, which bit of the semantics of this system language do I really care about? Exceptions, often I don't, because exception edges are everywhere in Java, and it's often nicer just to not have them because they do things that you don't care about. Similarly, with when we were talking about no base and no heap and things like that. But that, again, it comes down, am I just trying to track flow through local variables? Am I trying to reach globally through the heap? what am I thinking? So that we have, it's customizable in that sort of way. And the other thing that we have for, but on the other hand, as you said, the semantics do matter. You don't want to be in the business of simply arbitrarily constructing some graph that you think is probably the right edges. And one approach we have for trying to balance this is we have very flexible mechanisms of creating subgraphs. You could build a system dependence graph, and then you could say, okay, well, I want a subgraph. I only care about these nodes, for example, and give me all the edges. And there are different ways of constructing what you mean by edges as you delete nodes. Are they transitive or what? We have several different algorithms for doing that. So that would allow you to customize the graph in interesting ways. But generally, it's the case that if you have JavaScript, there's some basic semantics of the language that you should probably be following. And I'm not claiming that Wall is bug-free, but at least by design, the graph is a sort of conservative notion of that.
You may have sort of code bases that only, like, as part of coding style, restrict to a certain subset. Obviously, not doing anything too controlling. And maybe these conventions can be used to simplify the graph construction.
Then you have to be careful, because I have a coding convention, and I'm going to use that to JavaScript. But that would be like taking the semantics of TypeScript on faith. Should you do that? What are you looking for? What kind of bug are you looking for? Are you looking for malicious code that deliberately subverts this stuff? Right. In which case, you don't want to do that. That is something where you can certainly choose to do that. You could throw things out and say, I don't care about these edges, like filter it in different ways. But you have to be very careful. So what we have here is we have this graph. Okay, so I see a bunch of edges. I see there's definitely flow going from here. There's definitely flow going to here. So let's see. Maybe. So there's but we start with that. There's at least clearly the tainted data is going somewhere. Now, let's take vulnerable part. So now let's just say, okay, as a human, we can see. Start with this one. I go to the return. I come down to here. I go to here, and I go back to the right. So I can see that this is basic graph reachability, right? This is saying, here's this one end, here's another end. Give me all the paths. And while it has a bunch of code for finding things. So that is one level. And this, you notice, I happen to be picking an example where it works. It goes in here and then back here. Now, one thing to note, this is already not completely terrible, even though it's context insensitive, because this isn't a source of tainted data. So we're not even going to be looking for paths from that. So we won't ever see a path from this to a tainted sink, because we wouldn't even be looking here in the first place. On the other hand, we could imagine a path that started here and goes to this return, which would not be balancing the course of the returns correctly. We could potentially see it. Now, but that's a graph. Okay, I said graph reachability. I can do that. But so, as Joanna often asks, how do I actually do that in what? Okay, so we have this function get paths, and we have a graph. Now, as soon as I call graph, it's just a graph. SDG is just a graph. And Walla has this very abstract graph interface that is a super type of everything. So we're passing one of those. And now we're going to make this is a set of our results. It's a list of our nodes, because each result is a path, right? So it's a list of nodes. So we're going to make a set of those. And then this line basically says for node in G, that's basically for every node in the graph. That's good. Now, if we have an entry, now basically if it's a source, I'll get into this in a moment. But for every source, we're then going to build a path bundle. This is again a utility class in a while. Given a graph, you can find paths, which is give me a path finder. We have an iterator to start from the source, and we basically check everything. We filter for everything that's an endpoint. I'll explain endpoint finder in a moment. But basically, it's something that returns true if you'll notice an endpoint of the graph, a tainted source or a tainted sink. So we're going to find all the tainted sinks, and we're going to find, and then we're going to find all the paths from the source to any node that appears to be a sink. So then we're going to get our list of paths, we're going to add them to our list. We're going to add them to our test results in a minute. So this is a pretty straightforward way of using our BFS breadth first search pathfinder to find every possible path from each source to each sink. And because we're using a breadth first pathfinder, we have depth and breadth, but because we're using a breadth first one, we're guaranteed to get a shortest path as well, because it's going breadth. But as I said, so this is going to give us stuff, and this is quite straightforward, right? This is just a graph, and this is basically, you can pretty much parse the system dependence graph in. A system dependence graph built, as Joanna was showing with the options, with only the data dependence. Because if you use control dependence, you might potentially get all kinds of weird things here that don't make sense. So that's quite straightforward. And let me just show you, there are a few more pieces. I took this endpoint finder. How do we know what the source is? Well, we just assume somebody has told us this is your set of paths. Now, most people in this taint analysis, the sources and sinks are configured somehow by the user, and that this would basically be, this is the configuration that tells me that's the source. And then I want to show you, and then there's an endpoint finder for sinks. It's the same thing here. That's it. Basically, am I a sink? And then finally, we are accumulating our results. That's fine. And if you could see it, doesn't actually give you a path from the bogus source, right? Not a URL, because it's not a source. There's endpoint finder wouldn't find it. So that's not a problem. But the path, if you have context insensitive graph, the path from the source to the sink could potentially do things like go to the ID function from one call site and out a different call site. So you might get weird looking paths that are coming. We really want something that balances calls. We want something that really only looks at paths to the programming action. And that is not something like IFDS, interprocedural finite distributed subset, does. So who's familiar with the term IFDS? If anybody thinks they know and understand it, put your hand up. Just don't. Okay, good. So if you all knew about it, then these next few slides would be kind of pointless. So I am glad. So basically, we're computing, and so the difference is the key difference is for the graph that we saw just now, pathfinder. There is one graph that represents the data flow of the program. Then it kind of makes sense. This data program has data flow. This graph captures it. But so with IFDS, the key difference is IFDS is computing analysis of at each program point. So you can imagine a piece of code that builds something, had some value for I, and then the next statement adds 5 to I. Now the value of I before and after the add are different. So you'd have different properties of I before and after those two different program points. And that is the kind of thing that IFDS captures. And the other thing that it helps capture is what's called meet over all feasible paths, which is basically the whole balance call return thing effectively. And what we'll see is, if you want to think about it, how it works, it's when Joanna was explaining context sensitivity, how it separates data flowing from one call site and another call site. IFDS is another way of doing the same thing. You can think about it as an infinitely sensitive context sensitivity in a way. And I hope that will be sorry. So please stop me if anything I say doesn't make sense, because each of these slides does build on stuff. So how IFDS for our taint. So how to track taint. We want to keep track of all values holding tainted data. We must propagate taint for appropriate data. But we are building per program point estimates. And one of the things you quickly realize, taint analysis, is it's not useful to simply be told that some value is tainted. That's not useful, because what you want to understand is why. You want a path so that you can understand how, if at all, you want to fix it. So when we're building our program point abstractions, we aren't simply going to be keeping track of tainted values. We're going to keep track of a tainted value and the path from a source along which the taint flows. So that's the way to think about it. So our values, it's not just a graph of looking for tainted flows from a source of thing. These values are going to be much more complicated. Yes.
Question: Can concrete tainted value have actual multiple paths?
Sorry.
Can one tainted value have multiple paths, potential paths? Because you are just saying that we requires of value and paths to the tainted
Again,
source.
can a value, could this result have one value and multiple paths?
Yeah.
Yes, it will, in fact. Let me find the example. It will, right? Because this guy is ultimately going to have two paths, one from here and one from here.
Yeah.
But so yes.
And because in the slides there is just a path, so I was not sure if it can be multiple paths or single.
Yes, I will show you how that works. One moment. So, but you're absolutely right. We will see one value will have multiple paths. You can have, and of course, the paths aren't entirely disjoint either. The paths can share pieces. It can be. It's think about what you'd like to see as a user of tainted. So let's say when I get here, tainted data could have come from here or could have come like this. That's what you'd like to see, and that's what we're capturing. So we are going to track pairs of value. So let's see, how does that work? So let's start with one of the basics in IFDS, which is feasible path. So that's called. So this is the blue line is a call goes to return. And here are two paths, the green one and the red one. Both of them are paths along which tainted data flows from the return. But only the green one is a reasonable path continuing the blue one, because it's actually the same return of the appropriate call. This one is a return from a different call. And yes, this is also a tainted source, but there are two paths here. There aren't four, right? If we weren't balancing calls and returns, it would look like there were four paths, because we think we go from here to here to here, and that's not true. So there are two paths, and so that's what we mean by four. And IFDS, one of its strengths in the wallet implementation does this. It will give us that essentially for free. As it does its propagation, it keeps track of this for us. So you'll see, well, you'll think, wait a second, there's no context sensitivity here. How does it work? Well, IFDS effectively implements something that in this case is analogous to context sensitivity. So let's start with our own example. So IFDS and Walla works by analysis rules per, I'm calling it statement or instruction. I think Joanne, you call them instructions.
Yeah, I call them.
Possibly because that's what Walla calls them actually.
Yeah.
I just say statement with something. But basically, so the first thing we're going to do, let's start with this. We've read a tainted value, so this value is tainted. And because this is a source, the path is empty, right? This is taint just appeared from nowhere. That's a source. Now, what happens at the source? The first thing that happens at the source is it goes into this call instruction. And the call instruction, as we said, based on the JavaScript semantics, it ultimately calls this function. So tainted data has to flow from here to here. So let's just take a look. And we'll take a look in a little bit more detail about the Walla code that actually does that. But intuitively, what's going on is we're going to go from here to here, and the tainted values here is going to include the path that said this was the source. So the node will be X, the value will be X, and the path will include this document URL. And then the next step is we return that value. Now, we started from this one. So this is the only one we're going to go back to. And the IFDS mechanism will do that for us. As it propagates, when it propagates, this is the only one it's going to call. It's going to ignore the others because those don't bounce the force and returns properly. And now this guy needs to have a value that says, okay, text is the tainted value, and the path is this return and this read. So that intuitively is what's going on. Now, let's see what happens next. Then we're going to write, again, one from here. It flows to this call. And then this call goes over to here. So the tainted value and tainted. We must mark the return value. All right. Now, don't panic. This is not, there's not going to be a quiz. And also, a lot of this stuff isn't going to be necessarily useful. But I want to try and give you a sense of what you do when you actually write it down. So IFDS is written, I always say we were stepping from instruction to instruction, and what this function does is get, call, flow function. So what that's going to be invoked when a piece of tainted data gets to a call instruction. So what do? We said D1, this is, some of these fonts are a bit hard to read, I'm afraid, but anyway, doesn't really matter. This D1 here is the original, is a tainted thing coming in. So imagine in this case, it's telling me that I'm the document.url read with an empty one. Now, the first couple of things to remember. So we have our value numbers are integers, as Joanna said, and our paths. We're not really interested in the list of value numbers. That's not very useful to tell the user, right? What's the user care about value numbers set? However, what the user might be interested in is seeing the actual source positions of each statement. And that's what this is. So for every instruction in Walla, you can get this notion of a position for it, which depends on the front end. So bytecode is relatively poverty stricken. All it has is line numbers. But when you have source code, you can get all the way down to the exact file and the start and ending line and column numbers. So you can even reconstruct, and Walla even has utilities for reconstructing the exact source code that corresponds to this instruction. So that's what we're building. We're building up this list of positions. And remember, the example, the first one, the position list is going to be empty anyway. Now we've got to our invoke, which is our instruction, which is an invoke, it's our instruction here. And we're going to go through all its uses, and each instruction has some set of uses. And now we will just say, and remember, the first value in our little propagation thing here is the value number. So if I'm a use of the tainted value, then this piece of book, this is basically, don't read this in much detail, but basically what it's doing is it's getting the position of the invoke instruction, because to add to the path. So okay, this invoke added to the path, and then the next step is we add our taint. We want to say that the argument got tainted, and now we need to say the formal parameter is tainted too. And the way we do that is we know what the destination is, because that's what the dest block is telling us. And basically what we're going to do is we're going to figure out that my new value is I plus 1. So this is use is in, so for an invoke, and one of the convention is that if I have arguments 0, 1, 2, 0, 1, 2, 3, that corresponds to value numbers 1, 2, 3, 4 in the called method. Just for our own debugging sanity, we do not use 0 as a valid value number in the IR. It's not allowed. Because that way, if you don't initialize something, you can promptly trip an assertion. If 0 were a valid value number, there's no fundamental reason for it. It's just a lot for our own sanity. So that's why we add 1. Oh, what did I do?
Yeah, if you press the button to stop, I'll put play again.
Oh, put it back. Sorry.
That's okay. Well, we were here.
Okay, can you?
Very good.
Thank you very much. I pushed the wrong button. So what this is doing is it's figuring out, okay, I found a use in my instruction of this tainted value. I found the position of the invoke. I added it to the position, to the path of the incoming tainted value. Remember, the tainted value is a value number and a path, so I added to that path. And now I'm setting the tainted, and I'm telling the system, now there's a tainted value in the formal parameter of the method I'm calling, corresponding to the tainted argument. So that's one step of the call. Does this make sense to you? And as I said, please throw something at me if I say something completely confusing, because each thing does build. So
this part of the code doesn't handle, doesn't do anything but bounce calls and returns.
I mean, this piece of code.
Yes, doesn't do anything but.
No, it doesn't. It doesn't have to. That's the magic of Walla's IFDS.
I see. So if I were using Wall, I'd have to write something similar as well. Like this piece of code, I would have to write myself, but I wouldn't have to manage.
Well, if you wanted this exact piece of code, you can have it.
Okay.
But if you wanted an analysis that was propagating things through the core, through the program, yes, this is the sort of thing you'd be writing. But the thing to note here is, I'm not doing something like, I have this path, but I'm not doing something like keep dragging a call stack along with me so I can check the return myself. I don't have to do that. That is being done in the IFDS mechanism. But you just focus on writing, right? Given a tainted value that came into my invoke, I need to figure out where it was used and propagate tainted values in the callee. And I need to keep track of the invoke instruction's position in order to add to that path. So basically, all you think about is maintaining this, propagating these integer plus list of positions.
Julian, just a quick thing. Can you talk a little bit more on the basic blocking context, how to get these data structures?
Oh, that you get pretty much directly from the SDG.
Okay.
The SDG is in terms of that. Yes. Yeah, we didn't actually mention that.
Yes, I have not mentioned basic block. That's why I still can you.
So these are basic blocking context is the nodes in a system dependent span. And then there's the whole issue of the exploded ones, but we're going to go into that. This is more meant to give you a picture of what you'd be doing. So that's the cause. And now for the other thing that's interesting is return. So again, we have to figure out, okay, I'm going to return. I find my return instruction. And I don't have to check value numbers here because the return instruction in Java is only it only returns one thing, right? 0. The first user that it's returned. Sorry, that's tainted. Again, I have to get the position of the return instruction. This piece of code is exactly the same. And then what I have to do is I have to propagate this, I have to add that to the path, and then propagate it to the return value of the call instruction. And again, you say, wait a second, but this is again, we're doing, the IFDS is doing the balancing for us. So this is only going to be called for the right invoke instruction. And you don't have to worry about that. It just won't give you all those other weird ones. That there will be two paths, not one. So that, and the before X, so does that make sense? So what we've done so far is we've gone through the first taint analysis, the one that's rather simple, right? The one with using the graph reachability. It is simple. And it will potentially give you paths that don't work. This is, as you can see, the code is definitely more complicated. But what you get from that is more precision. And the IFDS that's implemented in Walla is based on research. So you might think, wait a second, that sounds expensive. Well, it's relatively cheap given what it does. It's based on research technology. A lot of it's from Wisconsin, actually, that does this efficiently. So those are two examples of how we might do taint analysis using Walla. And that's the sort of thing that often people who are more software engineering types who care about security, vulnerabilities, things like that, care about. You can imagine other things you could imagine checking. I don't know, you could do all kinds of code style things you could imagine checking this sort of property has. But that's taint. On the other hand, well, what's cool these days? Is taint analysis cool these days? Well, for some people it is, but what's really cool?
AI.
This is what's actually. So what are we going to do? So you've probably seen AI for code kind of things. People do something with the program and they shove it through some model and then they try to classify or something and do something. And there have been all different ways of trying to represent programs to learning. And I want to talk about two different kinds of things that we call AI for code. And one is understanding code and documentation. And one thing is understanding code by itself. And the simplest problem, as long as you don't think about it too carefully, is I have two programs. And I want to know if they do the same thing. Don't think too carefully about what that means, and it sounds simple. Okay, we're going to talk about that one first. We're going to figure out what we're going to do, just to give you a bit of a hint, is we're going to be using our Waller graphs and encoding them in GNN models to do something. But the other thing that's a lot of AI has had great success in natural language processing. And one thing to think about is it possible to somehow analyze code and documents? Can documentation tell us about the code, or vice versa? And then what we are going to do is this documentation reflect analysis, and we're going to try and correlate Waller graphs with text about code. In particular, we're going to be asking the code that looks similar in the call graph, does documentation about those pieces of code look similar to? The intuition you might think is maybe it should. So we're going to go through both of these. Yeah, but we started. So we started. So the two. Sorry, the two programs do the same thing. Well, first we have to define what we mean by program, define what we mean by same, and define what we mean by thing. Right? And what we're going to do, we're going to take a pretty simple example. We're going to say program means a whole Java program with main, with a main method. So the main method, a Java program in the most traditional possible way. And if you're not familiar with IBM's project CodeNet, it's a nice resource. It's a resource designed for this kind of analysis, actually. So each programs get a name starting with S, and they're scraped from public coding challenge sites. It's kind of like the sort of thing that Java students probably have to do, except that these sites are a lot dumber than what Java does. And each program solves a given problem. And so imagine a series of homework problems equals submitted solutions to those problems. So now, and the problem is verified by a given test. It is possible that some people might potentially use more than one test. Some people might do that. This data set, no, pretty much there's usually just one. And of course, the same, in this case, so there's an obvious meaning of same here, right? They have to solve the same problem, because we're told what problem it's trying to solve, so the meaning of same is obvious. For example, these two programs are the same. They solve the same problem. And thing, it means a test that specifies what the required output for some given input. So this CodeNet data set gives us very simple ability to define what we mean, concreted by program same. So now what are we going to do? All right. The short answer is this. All of these graphs, we're building things like SDG, you know, that acronym keeps cropping up, doesn't it? So we're going to take a program, we're going to build the SDG, and that's a graph. And there are lots, in fact, encoding graphs into machine learning mechanisms is its own area of research. But if you want, from our point of view, we're talking about Waller here, not machine learning. Really, we have a graph, and we have a graph neural network. Okay. We don't need to look at what goes on under the covers. That's what we're going to do. So we have a training.
Yeah, these buttons are kind of weird. Yeah.
My fingers are too big, maybe. Program. So we have pairs, right? Each program, the problem it's trying to solve. And we're going to classify basically take the SDG, take the problem number, and build a model. How can I predict the problem number from the SDG? And now, for the test data, we're simply going to take the program, build the SDG, run the SDG through the model, and see what problem number that gives us. So that's how it is. Now, I'll show you a little bit of code here. This is mostly stuff. This is basically building Waller. So Joanna had said she was going through the bytecode. You said there are analogous utilities for building call graphs for other languages, and that you're seeing some of them here. You see one for JavaScript, you see JS, that's JavaScript. You see Java, and this is actually the Java source code content. And then we also have Python. And then once we get these builders, Joanna had showed you a builder before, and these lines probably look somewhat familiar. Entry point node, make, call, graph. This is this machinery that Joanna had showed you. And this is the kind of thing you use that machinery for. And then the last line here, we STG to GNN files. It builds the STG, as Joanna showed you that code. And this is basically, just imagine it serializing it to some sort of JSON file that then the graph neural network is going to swap. But so this is sort of an example. This is, in a way, these lines are sort of the next piece of Joanna showed you building the call graph, the STG, and then this is maybe one more like it's one thing you potentially do with it. One thing that you didn't see before is stuff like this language, and that is Joanna had showed you bytecode, right? So that's always Java, but we have different languages here, and so we have we actually keep checking the language a little bit. That's something that's sometimes useful for encoding the graph, basically. And then once you do this, there's another piece of code written in Python, actually, that takes those graphs and shoves them to GNN, although that piece of code is not related to Walla at that point. Okay, I have a graph, so I'm not going to harm on that. Now, how does it work? Does this stuff work? Well, this is some experiments we did in a paper about CodeNet that was published in Europe. And this is the one that uses the code graphs, and these do not use graphs. This is really a data set. This was a data set track paper. This was meant more as an example of how you use this machinery. It wasn't meant to be saying this is the very best possible. So it's pretty good anyway, but there's more.
Julian?
Yes.
Can you please mention an example of coding task?
Sorry.
Example of coding task. But I saw the title of the paper is the application for learning diversity of coding tasks. What kind of task do you consider?
A diversity code, because this particular place where we use the code graph was pretty much the problem I had described, which is given the problems, which problem does a given piece of code solve? There are a couple of others that did not in that paper, because the CodeNet includes a bunch of stuff. This is one of them. There were a few others, but again, those others were not relevant to that. But in this case, it was the particular problem I was talking about earlier. Can we predict which problem a given solution is for?
What were the other techniques? There was the GNNs. What were they running? The other one.
So there are a couple of things that are somewhat self-explanatory. The bag of tokens and token sequences, those are a very textual encoding of the program. And these are also much more, these are based on more on parse trees than the semantics. And so there's a series of different representations of the program which are calculated problems. And as you can see over here, Walla does not do C++.
And the accuracy, so you mentioned that this is more about the data, not the efficacy of the technique. But it seems like the performance for Python is decreased. So is that maybe due to the fact that maybe Walla is more optimized for Java, or that was just a...
Yes, I think so. In fact, I think what's going on is that currently the Python front end puts a lot of the intricacies of Python into the IR. And that is probably something we would have to think optimize.
I see.
So yes, I think it reflects the fact that the Python front end of Walla is far less mature than the Java front end.
So when you mentioned that as we see C++ is not supported, so why is it supported?
Why do we not support it?
Why C++ is not supported by Walla, and are there some plans to maybe make it?
Okay, let me give you a sense of why, and then you'll understand where the answer to that question, the second question is. So Gianna was showing you things like, we talked about things like data flow through the heap. and the pointer analysis. Now, this is all based on some strong assumptions about the object. That is, I can access, I have a field, I can look at a field, I can look at an offset in an array. It really makes it difficult to think about the very unstructured way you can use memory in C. And there is a lot of work in point analysis for C, but that is that tends to have very different problems. If you think about C code, nobody uses the heap because the heap's really scary. The heap is basically a way of getting null pointer exceptions, trashes and stuff in C. On the other hand, there's a lot of, so there tends to be a lot of work in trying to understand which array index am I referring to. Was this pointer pointing ahead of that one? And there's a lot of work in that space, most of which is completely irrelevant to a language like Java or JavaScript or even Python, which really enforces memory safety fairly strongly. So you really have a very different, you focus on different problems and the solutions look different. It's not clear that doing those two things and calling them both Walla would actually buy you anything.
What about something like Rust? Would it be
Rust, I'm not that familiar with the details of Rust. I think its memory usage is much more disciplined than in C. Basically, anything with reasonably disciplined memory usage is the sort of thing that we're interested in. We're not going to do C, and we're not going to do assembly. So that was an example of what you would do. That was an example focused entirely on trying to use Walla to understand code and hand that in combination with some sort of machine learning. But there's more. The other thing that's become increasingly interesting is what about code and documentation? Now, this is this is a huge space. People doing all kinds of things, but I want to focus on one particular thing. So let's have a hypothesis as code that is used similarly that might have related aspects in its documentation as well. So think about multiple libraries that implement the same functionality under the same API. You would expect the documentation of those different frameworks describing the use of those APIs would have a lot in common because they are in fact trying to do the same. So our hypothesis, we want to see if this is true. So this, again, sounds easy to say, but it is easy to say. But so what does it mean for documents to be similar? So one of the things people do in machine learning with text is they compute this notion of an embedding, which basically takes each word or phrase and looks for, computes an embedding a vector essentially based on how those words and phrases are used across a very wide range of documents. So we can go textual embeddings for documents. And then we're going to use Walla to create metrics for code usage similarity. What do we mean by that? So this is some example. This is Python now. Again, this is sort of a piece of code that we can in fact handle in Walla. So imagine, this is what I mean by two APIs that do the same thing. These are both classifiers from machine learning. One of them is SGD and the other is this GLM thing. And they both produce a model, and the model allows us fit and predict calls, because that's what they do. You build a model with fit, and then you use predict to test it, to test values. And one of them also uses this score game, which is basically an aggregate of how well you did over a bunch of tests. Now, let's look over here. I have fit, predict, and score. The classifiers like that. If I just use fit and predict, well, I've got GLM. But of course, DSG classifier does that as well, right? You just ignore the score and then you have that. And so now our notion of similarity is going to be, for two pieces of code, we want as many of these as we can with the largest number of methods. That is, we want classes that are two classes that have wide shared APIs. But at the same time, we want to have as few classes as possible actually implement. Because think about it with toString or something. Everybody has toString. If you say these two classes both have toString, that's not useful. Everybody has. What you want is a method that only a few classes have. If a few classes have it, those few are probably related. That's the intuition. So as Joanna pointed out as we were going through this, it's sort of like TF-IDF, except instead of for the words, it's for these sets of method names. So that's what we're going to do. And this is going to be our metric of similarity. We're going to basically be doing, we're going to be building this set of stuff for two classes, and we're going to be doing essentially a TF-IDF notion, which classes are more similar. And for the documentation, we're going to use a language model of embeddings. And we're going to fine-tune the model using code-based tasks. So I only showing you one code-based task here, there were some others. And we're going to compare with them without fine-tuning. Let's just look at the result here. This is the cosine distance of the documentation text. This is the pair class usage distance, which is basically TF-IDF between the sets of class names that I have to put in. And this is what you'd hope to see, right? You hope to see that as the embedding of the text goes down, as that distance goes down, as the documentation is considered more similar by the textual embedding, the pair class usage distance should go down as well. That is, code with documentation that looks similar should have usage that looks similar to some extent. And that is, so this line at least is sloping in the right direction. Does that make sense, or am I smoking? Do you think that I sound like I'm smoking? You look skeptical.
I'm thinking.
Okay, thinking is completely fine. I don't do it much myself, but it's completely fine. But yeah, okay. So, but of course, if you do come up with questions, then of course you can always ask us. Now, so those are two uses of Walla. They're meant to be somewhat fashionable.
Yes, could you explain the different lines?
Oh, the different lines. Okay, sure. Basically, when I talk about embeddings of text and things like that, there have been numerous different models trained across different corpuses of text, and those correspond to these different lines. And basically, some of these lines are much more sensitive, seem more correlated to code than others. And in particular, these are things like BERT and CodeBERT are more trained. These are the fine-tuned models, the better ones, where you take the original textual embeddings and you fine-tune them based on coding tasks, so that your textual embedding is hopefully a little more aware of coding semantics. And that does make the correlation a little bit better. And if you're really want to know what the details are, or what these models are, how they were built, and so on, you can look at a AAA paper that describes these models in gory details. It also describes all the other code-oriented tasks. Those are code-oriented tasks. Those were about textual documentation, so they had nothing to do with Walla, so they're not included. All right, and that's kind of the end, which is good because we're just running out of time. So basically, but one thought I want to leave you with is that we were talking about what Walla is, how you can use it, things like that. But remember, Walla it's a living thing. Somebody built this stuff. And there's ongoing work. And one of the things you may have thought is, wait a minute, I have all this analysis. I can see this machine learning tasks and pay that something. I can see this taint analysis. But if let's say I had a taint analysis result that says, okay, this is bad, you should change your code this way. Now what am I going to do? We've said nothing about what could you do with this. Can I change the code? Can I generate new source code? What can I do? And the answer for now is mostly no, although there's ongoing work talking about code generation from the Walla IR. We built this somewhat language agnostic IR that tries to capture the semantics of the code. Can we turn that back into source code? And that's ongoing work now. And that has a couple of cool things about it. Imagine we support Java, support JavaScript. What if I built the IR from one language and tried to generate to the other language? I'd have a source-to-source compiler. And we're actually doing that, not for these particular languages, but I mean, it's more in the business of trying to modernize legacy software at IBM. But there's that, and similarly, suppose your taint analysis told you, oh, you should change the following, you should add sanitizers or something.
So question, how do you compare the cross-compilation, compilation to, for example, Graph VM from Oracle when they want to support multiple languages in the same virtual machine? So actually, they do not need to do the cross-compilation because they can just execute any of these languages side by side. So how will you compare these?
I mean, why would you use one versus the other?
Yeah.
Okay, so clearly, if what you want to do is execute a bunch of things, there is no need to generate source code. I totally agree. Why would you generate source code when you don't have it? Yes. But suppose what you're interested in, suppose you have code in one language, an old language. And what you want to do is you want code for a human to support in a new language, which one could imagine IBM would be interested in COBOL, for example. And one of the problems that COBOL has is most of its programs are dead. And that's a problem for supporting the code because dead people are pretty bad at that. So one thought is, what about if you could take the COBOL code and convert it into another language for which the programmers are still alive? That you can't do that with Graalvm. It's you executing the COBOL code is not the problem. It's going forward, changing the code, upgrading, thinking about it, understanding it. You really need source code.
Yeah.
So it's two different tasks, I would say.
Yeah, but it would require Vala to actually support more language. Yeah. So when you want to do the source to source compilation, then first you, for example, would need to support the COBOL, and then there is a question: why should we add support for COBOL when it's a dead language or language? It's kind of contradictory.
Now, there are lots of people for whom COBOL is of absolutely no interest whatsoever. Most people don't care about COBOL, and they can't, and they couldn't possibly care less, and they never will, and there's no reason. However, there are a relatively small number of people who do care, and one reason for that is actually every single one of us depends critically every day on COBOL code executed. Every bank, every government, every insurance. They all have lots of code. Much of it runs on IBM mainframes. So there are people who care. And some of those people work at IBM. Some of those people have something to do with Walla. And one could hypothesize that there are people at IBM who care about having Walla and machine code. You could hypothesize that. I am not going to try. But you're right that you need to support any language you want to generate, we need to support. Clearly, that's true.
Yeah, but just want to know, there is one more issue when you do the source compilation, because people would be asking, like, if the code you generated is actually equal in the behavior to the old, because the target language may be different from the semantics point of view, that some things needs to be expressed in the differently, some constructs. So and then there is always the question, like, if the previous way how it was described and the new approach to describe it in the target language are actually equal from the semantic point of view.
That's correct. So one big part of that is simply, that's basically the same question as, are there bugs in Walla? Of course there are. But by design, Walla is taking all these languages, putting them into this common IR. And so some level of semantic normalization in a way is happening there. And then there would be the same on the way back. But again, it's correct by design. I'm not giving Waller's bug free, but the mappings in and out would be correct by design. And usually you try to verify, you can try to test.
About the IR. So you map everything to this unified IR.
Yes.
So is the idea that if I write an analysis in terms of this IR, I can sort of apply it freely to between Java and Python?
Yes.
Or other, okay. So
let me walk back to this piece of code. The guy who's generating the file for machine learning, he doesn't even necessarily know anything. He doesn't necessarily know what language it is. He might, but he might not.
But that seems, so it seems to me like there might be some kind of, so my intuition would be there'd be some kind of conventions and things that might be presented in the IR that are specific to languages. Like Python, you might call an iterator method while you're looping through something. Versus in Java, you might just do indices and stuff. But I suppose that. So I guess my question then would be like, then isn't there a possibility of the IR being too complicated? So I want to just analyze Python, and then I have to sort of, my code which traverses over this generic IR has to handle constructs that might not even occur in my domain that I'm considering.
That's correct. So there's a trade-off there, which is, let's say you build an analysis, you decide how to make it work. You don't know the answer. Suppose your analysis is actually useful. How long do you think it is before somebody wants it on the other?
Right.
Now, there's a trade-off between and it's often because we all develop things, right? We start with a simple example, we build something that works for that example, and then you say, oh, cool, maybe this idea works. And then as you make the examples more complicated, of course, you have to add more cases and so on. The language would be similar, right? There would definitely be potentially new stuff. But the key point here is once you have this more abstract IR, it's true that there are obviously different languages and different conventions and so on, but there's a lot in common. And yes, there's always the trade-off as the more complete you want to make it, obviously things become more complicated. And there's more potential. One thing you've seen with ML is a lot of people talk about trying to generate documentation. I wonder if you could generate documentation from IR. I haven't tried that. So they're all kind of, it's an ongoing project. They're still alive. And of course, please get involved in building the future. Sorry.
May I ask one more question about generating IR?
Of course.
I think it's the main issue here is libraries, because some library exists for Python, for example. There is such library in languages. Is this IR somehow library must? How would you convert from one language to another? That's standard library.
Or worse yet, I'm doing a classifier in Python using sklearn, and I have something completely different over in JavaScript that's doing something. How would I map this?
Yeah.
Okay. So the way that sort of thing shows up in the Walla IR is with functions, with invocations. Now, I don't have a complete solution for that, but for what we did is we've already found stuff like that we need with our legacy variantization work. And one of the ways you do that is, as you build, you can look at the IR, you can see what functions it calls. Now, there is no magic that tells you sklearn is the same as this JavaScript one. But normally, if you want to do that sort of conversion, you have some specific problem in mind. And a person would have to tell you, okay, here's the mapping. In fact, there's a coding, there's actually an example of it already in our work. And it's not even between languages, it's actually between API versions in the same language. And somebody just tells you, here's the old API, here's the new API, here's how you take old code and convert it. We would build that into the code generation. Basically, you take the IO, you say, okay, find these old usage examples, turn them into. But there's no magic. I mean, it's not going to be, I have an arbitrary chunk of code, here's an arbitrary chunk of code in new language. Somehow it's magically using the right APIs. Somebody that does have to tell. But in our experience, when somebody wants a particular conversion, they typically have a very specific idea in mind. And they will tell you what that is. Okay, so other questions from either of us?
Have you tried to integrate some existing ideas?
Sorry.
Have you tried to integrate some existing ideas like code?
IDEs?
Yeah.
Yes, we have. Yes,
Yeah.
we have.
Magpie Bridge.
There's another project, a related project called Magpie Bridge, which is about taking analysis results. So I use Walla, other people have done other things with it, and using the language and extending the language server protocol to reify, to show it in different IDs. So both in terms of displaying things like problems that the analysis finds, but also extending language server protocol with a much more general HTTP, there's no HTML integration, because most IDEs have the ability to create a web view. And we have support for rendering sort of arbitrary stuff into web views that we use for things like configuring analyses and that sort of thing.
Yeah, so that's
So yes, there are projects. They're not really involved in projects.
that's the name of the project, Magpie Bridge.
Magpie
Magpie Bridge,
Bridge,
and
yes.
it's on GitHub.
Much easier.
Mhm.
Yes, this is built on the language server protocol, but it does extend it. Because the language server protocol is about showing analysis results and things like that. But often, as you will see, like Joanna was showing you the different ways you can configure the program dependence graph, the different forms of context sensitivity you can use, things like that. All of those potentially show up as configuration options, which we can then capture in a web view. So and we could actually do, so yeah, you could actually build fairly flexible, we've shown examples of building fairly flexible integration of Walla into whatever IDE.
So does this integration actually assume that the Walla is running on the same machine as the IDE? Because we have tools that run analysis to replay based on the SLC standard. And we were some people were asking if we were looking at language server protocol and make it to it. And one issue which we keep seeing there is that all the integrations are kind of assuming that the IDs and tools are running on the same machine, and they are actually synchronizing or exchanging the code through the file system directly. And so are there other options how to?
Yes, so fundamentally the language server protocol is based on a JSON RPC protocol, which, I mean, it's RPC, it's meant to be channeled. In fact, it looks remote even when it's local. Now, yes, if you just give it a plain file name, then you potentially, I mean, if you have multiple machines with a shared file system already, you're probably good. But if you don't have that, if you don't have a shared file system, then yes, we even have where the language server protocol actually passes big chunks of code around if you want it to. So you can actually have, you don't need, you can make it independent of the file system if you want.
Okay, and
There is some overhead with that, more copying.
yeah. Well, of course, we see the overhead also in our solutions.
Sure.
So we have various ways how to actually handle the files. But we're just looking how to we can potentially integrate with the language server protocol. So are there some examples we can look at which are using let's say sharing or exchanging the data remotely, not through the file system?
Yes, in fact, we have examples of that. Let's see, do we actually do that? Yes, actually, if you look at some of the examples of what integrated Walla value with the language server protocol, we do that.
And it's in the Walla GitHub, or
It's in the Walla GitHub. That's right.
Walla.
There's a Walla GitHub. There's an examples project.
Okay, great. We can look at it because my student was looking into the integration. I was seeing that he sees everywhere that it's just done through the file system, and it's when not doing through the file system,
We actually
complicated or problematic.
in Walla we actually have ways of as we move, we send the file and we build a little widget that you send the file somewhere else, and that in the other place it has a different name and so on. But we have enough breadcrumbs that we can map the names all back to the original. So it moves somewhere else, and by the time you get the analysis results back, they get mapped back to the original names and positions.
Okay. So definitely look at it.
It's
Because, currently, we are usually doing that. We are parsing the results of the analysis back, and
One place you might want to look.
transforming them into Eclipse markers to link it back to the editor. So people were actually asking if the language server protocol would be another possible solution.
It would, and that's what we use. In fact, this one in general, this is the so the name is Chinese character. So Magpie Bridge is already a Chinese name, and it came from the fact that so it's Qichao in Chinese, roughly, and it turns out that at the time we were working on this project, you may remember the Chinese sent a space probe to the far side of the moon. Now, the moon is kind of big and solid, so radio waves don't get through it very well. So they needed a relay satellite to communicate. And that was called Qichao. And it was taking it was helping these two rather disparate things communicate. And we thought that was a nice analogy. So we called it Magpie Bridge. And then the taint analysis project is called Zhenu, and that is actually Zhenu is a goddess from Chinese mythology who actually is one of the people who crossed the Magpie Bridge. So which is
Great, thank you.
anything else we can tell?
An idea has already their own for the analysis.
Sorry?
Modern ideas already has their own for the analysis, static analysis, like better format,
Which one has?
any modern ideas.
Okay, sure. Yes.
They didn't have how they perform something.
They typically, none of the IDs that I know of do the kind of point analysis that we're talking about. If you look at Eclipse or IntelliJ, things like that, the level of analysis you typically get is what Joanna was showing you with class hierarchy analysis. If you remember, which is typically even RTA is not something.
There is some security tools like Sneak. Then that's taint analysis.
They do. They focus much more on local issues. Simply because they don't understand what the callback itself is. So that's the big difference. And in terms of actual bugs, well, it's probably the case that most errors are done local things. That's probably true for secure taint analysis. However, the key for taint analysis is you have an adversary, right? Malware. you say, well, most people do X. That's irrelevant for now, because Malware is not going to people precisely not do. It's anything that's common, they'll do something else because they have to, or it's just random. Or you might, I mean, it's a never-ending answer. Analysis needs to get also needs to get but we are not in the business of building a change analysis problem. We do not do that. So, is it possible there are lots of things they find that we don't? Yes. But again, we're not a company that sells it.
Do you have a sort of formal description of the semantics of the Walla IR, and have you considered sort of using that for verification, validating maybe translation?
Short answer is no. The long answer is also no, but the long answer is that, in a way, one of the motivations for trying to do these sorts of tutorials and things like that is to gradually build ourselves more documentation describing what's going on. And one of my great hopes is that Joanna's students are getting started to be able to do that. But the short answer, if you would say what's the biggest flaw in Walla right now, I would say it's the documentation, right? Okay, is there anything else? Going once, going twice. Well, I think we both are very happy that you came. That I think it's been a useful discipline for us to put this together. And so thank you for listening, and thank you for providing us for your questions, and we will thank you for any feedback that you prefer. You could give us if you have comments about things that we should potentially have included that we left out, or things where we went into detail where it's kind of obvious and we shouldn't have. We would definitely love to roll forward with that. Thank you.
I have some feedback on the slides.
Sorry?
Don't use yellow text over white
Yes,
background.
that is correct. Yes, I realize. That was caused, I think that was probably I copied code that was from a different background color.
Yeah, it was darker.
Yes. I think so.
Yeah, you ever said series of pastel colors like light green, light yellow, light
Yeah.
orange?
Yes, this is true. Yeah, you're correct.
Are the slides available somewhere?
The slides available.
The slides
somewhere.
No,
good
but
question.
I can put on the repo if you want. So I created a repository for this called FSE 2022 Walla tutorial on my account. I don't know if you can see. And I can put today's slides there.
Great.